Thank you very much for coming. It's our great pleasure to have Sherwood Andrew here with us. Sherwood did his undergraduate in University of Virginia, and then he did his PhD at Caltech, after which he had a postdoc at NC State and jointly with Berkeley, and currently he's an NSF fellow at Berkeley. During his career, Sherwood worked on simulations and was always interested in radiation transport and neutrino transport. In his spare time, Sherwood is a pilot. He is piloting planes and paragliders. Thank you so much. And he's also doing a lot of outreach. During his graduate school, he was, and I guess NC State, he was tutoring foster kids. And now he is inspiring people in El Salvador to study astrophysics. And he goes to Salvador and gives lectures in Central, and he learns Spanish for these purposes. So without further ado, Sherwood, tell us about neutrinos.
Well, thank you very much for the kind introduction, and thank you very much for inviting me here. It's been a fantastic week so far. So I'm excited to have the opportunity to talk about some of my work in some of the really interesting neutrino microphysics that goes on in explosive astrophysical environments. It's focused on neutron star mergers, but it really is applicable to both supernovae and neutron star mergers. So this here is this pretty picture was actually produced by an undergraduate that I worked with. She's now gone on to graduate school. This is a snapshot from one of our simulations of neutrino flavor transformation, but we'll talk more about that later. So just to start as broadly as possible, the night sky is deceptively tranquil, although we know that if we look closely enough, it's filled with transient events. That is, things that become bright and then become dim again. Now, because of the obvious astronomical distances to these sources, these relatively dim transients actually represent some of the most extreme environments in the universe and some of the most violent explosions in the universe. And so what we want to do is use the huge wealth of modern resources available to us to try and understand a lot of the open questions in physics and astrophysics that these systems can help us with. So there are a growing number of increasingly sensitive and increasingly fast transient facilities that can observe these transients that are increasingly rare and fast that would otherwise be impossible to detect. There's a huge number of telescopes across the electromagnetic spectrum from which we can get very detailed information about the light coming from the exteriors of these explosions. In order to dig down into the interiors of the explosions, we need to use tools like particle detectors and gravitational wave detectors. So if these sources are sufficiently close, it's possible to detect the fluctuations in space-time and the very weakly interacting neutrinos that come from these sources. And then, of course, there are our experimental capabilities are also growing in ways that can help us probe a lot of the microphysical processes that happen in these extreme environments through, for instance, this is EFRIB, one of the new particle colliders that is constraining a lot of the properties and reactions between very heavy nuclei, which is important for understanding a lot of the nuclear reactions and nuclear processes that happen. And so the goal, like I said, is to try to use all of this information to understand some of the big open questions in physics and astrophysics, like how are the heavy elements in the universe made? How does matter behave at extreme densities? What is dark matter? Do we need new physics to describe what we see in the universe? And what processes are driving the evolution of the universe? So let's look at one of these, the origin of heavy elements in the universe. So as Carl Sagan famously said, we are made of star stuff. But what does that actually mean? So if we look at the lowest mass stars pretty similar to our sun, they burn hydrogen and helium and increasingly more heavy elements until they, at the end of their lives, they shed their outer layers and disperse many of these elements into the surrounding area and leave behind a white dwarf. The elements that are fused at the cores of these stars are can form some lighter elements like carbon, oxygen, neon, some of those elements. And then the remnant white dwarf, if those explode in a thermonuclear explosion, you can create elements up to iron, but not much farther. So what about the more massive stars? If we have stars that are above something like 10 solar masses, at the end of their lives, so they're able to fuse elements in their cores up to iron, and by some process, those cores collapse, leading to an explosion, and you eject a lot of this matter out. And so once again, you're able to create elements up to about iron or so. So what about the most massive stars in the universe? If you have stars that are massive enough, you can undergo a hypothetical type of explosion, a para-instability supernova explosion. But once again, this is expected to produce elements only up to about iron or so. And so one of the big questions is, if all these processes produce elements up to iron, but we see gold and platinum and all these heavy elements, how does the universe actually make those? And so the clues for this come from nuclear physics. So we can look at a plot of the abundance of various elements. On the horizontal axis is the weight of the atom, and the vertical axis is the abundance. And so on the left, there's elements up to about iron or so. So this is the iron peak elements that come largely from supernova explosions. But then beyond the iron, there's this interesting structure of abundances where you have there's a variety of peaks, and they're marked here with R and S. So it turns out, in order to make those peaks, we need neutron capture processes. So if you have some seed nucleus and you add a neutron to it, you can make heavier elements with that. And so what we need is some astrophysical environment that has neutrons. And so this is something that we really only know by mapping out a lot of these nuclear reactions experimentally and theoretically. And so this is insight that really wouldn't be possible without advances in fundamental nuclear physics. So if we have astrophysical environments, we want to find a source of neutrons with which we can make all these heavy elements. So naturally, we know that the slow neutron capture process, that is, if you have some seed nucleus, you can add a neutron to it and it's unstable, it will beta decay back to a stable element, and you can do that over and over again, slowly building up more and more massive elements. Those conditions are actually satisfied in low mass stars. And so that's where we expect a lot of these the so-called S process elements to come from. But if we want to produce the other peaks, the peaks labeled with R, we need a very rapid neutron capture process. So you need to accrete neutrons much, much faster than the atom is able to decay. And so you build up these giant globs of neutron-rich nuclei, and those decay back into and form those other peaks. So in order to do that, we need an astrophysical environment with a very high density of energetic neutrons. And so where better to find those than an entire star made of neutrons? So then the question is, if you have a bunch of neutrons in a neutron star, how do you get them out and how do you form elements from them? So there's two places where this historically has been a very, very popular idea for how this happens. If either during the formation of a neutron star, which is an explosive event, or during the collision of two neutron stars, which is another explosive event, you can inject this neutron-rich matter. So let's see what this actually looks like. When neutrons, so if you start with a massive star that has a very large iron core, so you can see on the bottom right is the abundance of iron. So everywhere that's brown is iron, and it has a radius of a few thousand kilometers. Once it's massive enough that it's unstable to gravitational collapse, within a couple hundredths of a second, it will collapse to a fraction of its size. And if we zoom in on this, this collapse suddenly stops once the densities reach nuclear densities. The strong force comes into play and very rapidly slows down this collapse in such a way that the rest of this star is still supersonically infalling and forms a shock wave that starts propagating out through the star. One of the big mysteries of core collapse supernova theory during the past several decades is how you can actually energize the shock to go through the rest of the star. Because without, if you just look at the that shock wave propagating without any other additions, the rest of the star is infalling far too fast, and it will push that shock wave back in because the shock wave can't move through the matter as fast as the matter is falling in. And so you, rather than an explosion, you just have everything accreting and forming a black hole. And so one of the big questions is how you use this, how you use the microscopic processes present in this explosion to re-energize that matter and send the shock wave out. And so there, it's really only been in the past few years or so that this has been, that theory groups have started to see success in first principles, three-dimensional large-scale simulations of core collapse supernovae. And so this is, you know, there's several groups around the world, especially nearby in Princeton, that have been producing some of the most advanced self-consistent models that actually show explosion. So then that leaves behind some remnant neutron star, which cools over a period of many years. So there's a variety of, so we want to understand the processes that are going on inside. And so we can probe those through a variety of mechanisms to understand the dynamics just under the shock. We can observe when the supernova explodes, it leaves behind a remnant, and some of those dynamics are reflected in that remnant structure. Further inside, so in this region that's very hot and emitting a lot of neutrinos, the neutrinos, the canonical theory says that these hot neutrinos are able to carry energy from the protoneutron star to just under the shock, depositing enough energy that it's able to send that shock wave outward. And so if the star is nearby enough to detect with neutrinos, we can probe that region of the supernova. And the most dense regions are hopefully going to be probed in the future through gravitational waves. So if this matter is very quickly moving, you can distort spacetime enough to see the signature in LIGO or next generation detectors. Essentially, only if the galaxy or if the supernova is optimistically within our galaxy, realistically probably even closer. And of course, in order to put all these pieces together, we need large supercomputing applications in order to faithfully treat the equations that we say are important for reproducing these processes. So then we talk about the death of neutron stars. The canonical story is you have two neutron stars that are orbiting, and the orbit decays because they're emitting gravitational radiation. At some point they contact and eject a bunch of material in all directions. What's left over after the fact is a compact central object, either a black hole or a temporarily stable neutron star, surrounded by a very hot, very dense accretion disk. And so there's a variety of processes that are ejecting matter. The first is this initial tidal shredding of one or both neutron stars that ejects a bunch of relatively cold neutron-rich matter, largely in the equatorial direction. In addition, the disk is very hot and evolving viscously or really through magnetohydrodynamic stresses, and that's sending a bunch more matter in all directions. And so these are observable as via a kilonova afterglow. In addition, there's a relativistic jet that gets launched, either most likely through magnetohydrodynamic stresses, but there could be some impacts from neutrinos as well. Now, the upshot from these simulations that I want to stress is that neutrinos play fundamentally important roles in both of them. In supernova, they are the driving mechanism behind the explosion, and the neutrinos are, if the supernova is nearby enough, they're detectable in Earth-based neutrino detectors. In neutron star mergers, the neutrinos determine the cooling rate of the disk. They also heat up the outflows, and they determine, because neutrinos can change neutrons and protons and vice versa, they are what determines the abundances of the elements and the abundances of the neutrons that are ejected in the outflows. And so understanding the dynamics of the neutrinos is very important, and especially the electron neutrinos, because so I mentioned that neutrinos can change neutrons into protons and vice versa, but really it's only electron neutrinos that can do that. And that's because they are able to interact with charge current processes. So electron neutrinos can interact with nucleons and create an electron, because the mass of an electron is something like a half an MeV. The characteristic energies of the neutrinos are something like a couple tens of MeV. So there's plenty of energy to create lots of electrons. There's not really enough energy to create a large amount of muons or tauons, because they're just too heavy. Some get produced, but not. The point is that electron neutrinos really play a special role. And so we know that it's very important to understand how the motion of these neutrinos interplays with the dynamics of the disk. So this is just comparing two different numerical treatments of the neutrino transport in the disks. One is a Monte Carlo transport method, which you should see is more reliable, and one is a two-moment method, which is an approximation of the transport scheme. This plot here shows an abundance as a function of the electron fraction. So farther right on the horizontal axis means it's a more equal mixture of protons and neutrons. Farther left means you're more neutron rich. And so the point that I'm trying to show with this plot is that under the particular numerical treatment of the neutrinos can have a significant impact on how neutron rich your ejecta is, which likewise means it can have a significant impact on what kinds of elements you're able to form in that ejecta. And so this is another comparison using two different numerical techniques. This one, it doesn't have, this work doesn't have Monte Carlo transport. This is two kind of moment-based techniques. And the point is that, so the different color curves show the abundance of different elements as a function of mass number. And the point is that there are significant differences in what kinds of elements you can make compared to the black dots, which are the solar abundance of these heavy elements, or the solar system abundance of these heavy elements. So the point is that we need accurate neutrino transport in order to have reliable predictions of the abundance of elements that these systems can produce.
In that curve, none of them match solar.
Yes.
Is solar the answer you want? Is that supposed to be the right answer, or?
Yes, the goal is to match solar. There's so this is the solar abundances are very well determined. You can look at the abundances of our process nuclei in other stars, and the error bars are significantly larger. In most stars, if you have all the elements produced, it is a very robust signal. Like the particular structure is very robust. There can be a lot of variation, especially in the lighter side. So maybe to the left side of this, I should do this. To the left side of this peak, there can be significant variation there. And so there are astrophysical uncertainties related to the rates of various processes that can either produce the whole range of elements or only part of them.
So is it thought that this discrepancy is primarily due to the neutrino transport mechanism, and therefore these methods that David is looking at are not still need improvement because they're not agreeing, or is that the takeaway we should take?
Yes and no. So I think that the variability between the methods says that that there's still work to be done. The difference, especially in the light elements, the difference between the abundances of the calculated elements observed could be a statement that that neutron star mergers are not the only source of these heavy elements. There could be other things producing them. Okay. So yeah, that discrepancy is not clear.
Okay.
There's also some ambiguity in the nuclear rates.
Yes, that's true.
Okay.
Yeah, so that's something that hopefully facilities like EFRA will be able to make significant progress in that. They won't be able to map out all of the rates, especially with the more unstable elements. Those still have to be treated theoretically, but yeah, at least it should get a lot better in the coming decade. Okay, But so far we've been a little bit naive in talking about neutrinos. We know that there are 3 kinds of neutrinos, but it's not true that if a neutrino is born as, say, an electron neutrino, that it stays an electron neutrino wherever it goes. We know experimentally that neutrinos change flavor in flight, and this is a result of the fact that different neutrinos have different masses, and the quantum state describing a particular mass is not the same as a quantum state describing a particular flavor. And so when we talk about neutrinos, we really need to talk about a superposition of quantum states, which we represent here as a quantum density matrix, where the diagonals of this quantum density matrix represent the probabilities that neutrino is each of these 3 flavors, and the off diagonals represent the quantum coherence between these different flavor states. And so, like I said, this is something that has been determined experimentally, and there are still some significant uncertainties in the fundamental parameters describing the mixture between these quantum states and neutrino masses. But again, with some exciting experiments in the coming decade, the hope is that a lot of these parameters will be really nailed down, and so there's we know we have limits on the sum of the neutrino masses. We know the differences between the different masses relatively well, but there's still uncertainty in like which neutrino is the most massive. So this is the hierarchy problem. So they could either be normal hierarchy or inverted hierarchy, just describing the fundamental parameters of neutrinos. So upcoming experiments should, well, they're supposed to nail a lot of those parameters down. And so this will become much more a precision science in the coming years. Okay, so how do we think about these quantum neutrinos in core club supernovae mergers? So at least I, as a simulator, think about all of these different elements that go, all the different matter in these simulations as chopped up into little cubes in the domain. And so the way this is done with ordinary matter, like neutrons, protons, and electrons, is you have some cube, which is a small piece of your domain, and you can represent that with some average quantities, like the average density, the average velocity, the average fraction of neutrons and protons, the magnetic field, and the space-time metric in that small piece of the domain. And so if you want to calculate how matter flows from one part of the domain to the other part, you compute exactly that. You compute how matter flows from one cell in your domain to another cell. And the way this is done with hydrodynamics is so that the density evolves according to conservation of mass, and the velocity evolves according to conservation of momentum. And we close this with an equation of state that says, given the average properties, we know what the pressure should look like. For neutrinos, it's more difficult because the neutrinos are weakly interacting enough that they're not in equilibrium, so we can't prescribe a particular equation of state to the neutrinos. In addition, the neutrinos, like I mentioned, are quantum particles, and because if you have a neutrino that's a particular flavor, say electron flavor, this is a quantum superposition of different masses. And different masses move at different speeds. And because of this, the quantum wave functions for these different states decohere. And so there's phase effects that manifest themselves as oscillations in the average flavor of that quantum state. Going into how we think about this theoretically, the quantum kinetic equations are the most simple equations that we can use to describe the evolution of quantum particles in these systems. So the left-hand side is the transport term. So this just says that, this distribution function represents the number of particles, the number of neutrinos that you have at each point in space, moving in each direction, and with each quantum state. And so the transport term says that if you look at the number of neutrinos that are moving in a particular direction at a particular location, it changes because thing because the neutrinos themselves are moving. On the right-hand side, the collision term says that that number of neutrinos changes because they interact with the background matter or with other neutrinos, and they can get absorbed, emitted, they can change their momentum. And the term on the right is essentially, this is just the Schrodinger equation, says that the quantum state of each neutrino will change according to the Hamiltonian or the potential that it feels. So let's see, so what does this look like? If we, for now, ignore the transport term and we ignore the collision term, we're only looking at something, we're pretending it's completely isotropic, and we're only thinking, in this case, about the Hamiltonian that a particular neutrino feels due to its mass. And so this is, like I said, this is because different masses move at different speeds. You get this effect where the flavor oscillates with time. So the picture on the left here is a Bloch sphere. It's a quantum Bloch sphere. And an arrow pointing up means it's an electron neutrino state. If it's pointing down, it's a muon neutrino state. And it changes because there's a potential, which you can visualize as a vector diagonal here. And the quantum state just orbits around that vector just because of the Schrodinger equation. On the right-hand side, I have a couple of diagrams of the distribution. So you can see this density matrix. You have the values of the number of electron neutrinos and muon neutrinos are oscillating a bit, and the off diagonals representing the quantum coherence are fluctuating as well. And so that's just for a single neutrino changing because of its own mass. We can also include collisions and include interactions with other neutrinos. And so this becomes a nice nonlinear problem with a very strong separation of scales in the sense that you can see that, so this, the red and blue lines show fluctuations of the diagonal parts of this quantum state. And so that's fluctuating so quickly that it's just filling in that curve. So it's, that's the effect of the term on the right-hand side. These fluctuations change in amplitude due to the collision term. And so you can see that the fluctuations in general are occurring much, much faster than the collisional processes. And so this makes it a rather difficult problem to treat because so ordinary transport is what we use to try to treat the motion collisions of these processes. But we know that the quantum fluctuations are much, much faster. And they interact together. So if you write down the collision term, it also has a quantum mechanical structure that determines how both the diagonals and off diagonals of this quantum state evolve in time. So they're not generally separable. So we can look at, there have been a large number of flavor transformation mechanisms that have been suggested over the years. The most simple is vacuum oscillations. This is, once again, just due to the fact that neutrinos have mass. So in vacuum, neutrinos will change flavor because they have mass. This is something that occurs anywhere from the source through the detector. So, so anything that emits neutrinos, we expect the neutrinos that we see to be a combination of flavors. There's also the MSW mechanism, which comes from if we add the fact that neutrinos are moving through background matter, the neutrinos see that background matter and feel it as a potential, which goes into that Hamiltonian describing the flavor state change. There's a particular density at which the vacuum term and the term from the masses and the term from the matter roughly cancel out, and that that's the MSW resonance point, and you can get very significant flavor transformation. So although in the vacuum case you saw there was a relatively small amount of the arrow moved relatively small distance on the Bloch sphere, when you get to this resonance point, you can have significant flavor transformation. But I'm showing in this diagram that generally occurs far away from these engines. So you don't expect it to be important for the supernova mechanism. You don't expect it to be important for neutron star merger nucleosynthesis, just because the densities where those explosive environments are the high densities in those explosive environments put the resonance are way off resonance because the influence from the background matter is just way too strong. So then we can talk about neutrinos are not only moving through a background of matter, they're moving through a background of other neutrinos. And so the fact that neutrinos interact with other neutrinos, you can get other interesting effects, which also come into play when you have approximate cancellation between this neutrino potential and the potential from the masses, which can again lead to very significant flavor change. Now, this was originally very exciting when it was proposed because it can be important much farther inside, much closer to these dense environments. But detailed calculations have shown that we really don't actually expect it to be a significant impact on supernova, the supernova explosion mechanism, or neutron star mergers as well. But then there's a variety of other mechanisms. So one that was proposed in the past decade was this so-called matter-neutrino resonance, which is an approximate cancellation between the potential from interacting with other neutrinos and the potential from interacting with the background matter. And this occurs primarily in the polar regions in neutron star mergers. And this has been hypothesized to lead to significant impacts on the abundance of elements that can form from mergers. Then there's also the so-called halo effect, where neutrinos that are escaping from a supernova, they can scatter off of the heavy elements that are present in the envelope of the star. And even though it's only a relatively small number of neutrinos that are scattered back, there is this diffuse halo of inward moving neutrinos, and those can drive flavor transformation. But again, this is something that happens largely outside of the most important dense regions. Recently, the so-called fast flavor transformation, it was proposed back in around 2005, but it was only about a decade later that the field actually picked up onto it and started applying it to realistic supernova merger calculations. But this is, you cannot see that on this. It's supposed to be yellow throughout. People online can probably see it better. But so it's the point is that this fast flavor transformation is due, or fast flavor instability is due only to neutrinos interacting with other neutrinos. And and this can happen essentially everywhere in both systems. So it's been shown to happen outside of supernova shock. It happens inside of supernova shock. It's supposed to happen inside of the turbulent core of the supernova, and essentially everywhere in neutron star mergers. And so this is exciting because we know there's a flavor instability that will change flavor, but the details of this are not very well worked out. And that's what I'm going to try to probe with the rest of the talk. And so there have been some preliminary investigations into what this actually means for the nucleosynthesis of elements from neutron star mergers. This is some work that I'm working on with Rodrigo Fernandez, doing some disk simulations and looking at how some approximate treatment of flavor transformation can change the abundance of neutrons in the ejected matter. And so this has a relatively small effect, but there is dependence on the particular model that's chosen, either your choice of the disk mass and the black hole mass, or your choice of the constituent merged compact object masses, and how long the hypermassive neutron star can live, which depends on the equation of state, and a variety of other factors. And so I guess the point is that we're starting to show that there are significant, but not necessarily game-breaking changes that come from neutrino flavor transformation. And I should say that this is not even an approximate treatment of flavor transformation. This is a hack for flavor transformation that's just designed to probe whether the results are sensitive to flavor transformation. But a lot more work has to be done in order to figure out how flavor transforms to actually do this reliably, rather than just make as big of a changes as you can. So that's just doing the flavor transformation. I mentioned that the collisions and flavor transformation are important, and they both modify this quantum state. This is some other work that I've been toying around with. This is taking a snapshot of a three-dimensional neutron star merger calculation. You can shoot rays through it and calculate the there's standard ray tracing. You can calculate the change of the neutrino abundances along each of these rays. In addition, you can calculate the flavor transformation along those rays. And doing exercises like this, we can show that collisional effects and flavor transformation effects indeed are happening at the same place and at the same time. And so you cannot in general treat them as separate processes. They really are happening together. Okay, so now let's talk more about this so-called fast flavor instability. So there's a huge amount of work in the past several years that's gone into this, starting with linear stability analysis. So you can look at a particular point in your neutron star merger, and you know the distribution of neutrinos in momentum space. And you can ask, is this actually unstable to rapid flavor change? And so you do standard stability analysis, and you can come up with a dispersion relation that says, for different wavelengths, you expect different growth rates. And so this type of analysis has been used to look at simulation results, and you can find the locations in the simulations where you expect instability. Now, this is only linear analysis, so you know that it's unstable, but you don't know the nonlinear result. You don't know the saturation amplitude, or equivalently, how much flavor actually changes. You just know that there's going to be some exponential rise in this flavor transformation this time. And so, at least up to this point, there have been some very limited local flavor transformation simulations, where you do something like you assume that the universe is homogeneous and isotropic in all but one direction. And so you do that sort of toy problem, and you can show that the flavor instability does manifest in these systems as you would expect. So at least until recently, this was done in very limited systems. So one of the main goals of my work is to try to understand this instability well enough that we can actually understand what it's going to do in neutron star merger and supernova environments. But before we go too much deeper, so this is an instability. It is a plasma instability, just like other plasma instabilities that we know about. So this is showing the classical two-beam instability. So you have this is showing two beams of electrons moving against each other. So that's this velocity. So there's electrons with negative velocity and electrons with a positive velocity, and they're distributed over space. So initially, it's just you have a domain with two beams moving against each other. If you let it evolve, the small perturbations in the electrons create perturbations in the electromagnetic fields, which themselves feed back into perturbations on the electron motion. And so these initially two distinct momentum groups get mixed together through this plasma instability. So the exact same thing happens for neutrinos, except instead of having mixing the momentum, you're mixing the flavor. So in this case, we once again have two counter-propagating beams of neutrinos, but one is electron flavor, one is electron antineutrinos. And so the same sort of thing happens. The small perturbations in the neutrino flavor create perturbations in the Hamiltonian that drives the quantum flavor change, which in turn drives the flavor change of each neutrino. And so you see something similar where there's the instability grows and then it saturates into a nonlinear mess of all the different flavors. And so I and some of my collaborators wanted to do this not in a toy model, not in a sort of artificially restricted geometry of the universe. We wanted to actually be able to take situations inside of neutron star mergers and supernovae and see what that flavor distribution would actually do. And so this is largely something I would not have been able to do this without the help of Don Wilcox, who is now he's staff at Lawrence Berkeley Lab at the time. He was just a postdoc, but yeah. So this is because this is a plasma process. we had the idea that, well, maybe we can use the same methods that are used for plasma physics and apply it to neutrino flavor as well. And so we wrote a particle and cell code using the Amrex framework. So it's beautifully performance portable on GPU and CPU systems. But the way that it works is you represent your radiation field as a bunch of individual particles, which are present in a background Cartesian grid. The Cartesian grid collects the Hamiltonian information. So you just sum up from all different particles. And so within each grid, you know what the Hamiltonian is. And then each particle evolves according to the Hamiltonian that it feels. And so each particle has its own quantum density matrix. And so as the particles translate in space, their quantum density matrix changes according to the potential that it feels. So you initialize the particles, you deposit the potential, you use that potential to evolve, and you repeat until the simulation's over. And this actually works fantastically well. This is a toy problem where we have a broad beam of neutrinos moving one way and a broad beam of antineutrinos moving the other way. We know analytically what the dispersion relation looks like. And so you can look at the growth of flavor transformation. And so this blue line here shows the fastest growing mode from analytic linear stability analysis. And these purple and green lines show the flavor transformation that grows at exactly the rate that we would expect. So yeah, this method works very, very well. And so the goal now is to answer the question, well, how much does flavor actually change in these systems? And so this is an example of a three-dimensional simulation where we can just pluck out the radiation field information from somewhere in a neutron star merger or a supernova and simulate it. This is showing the complex phase of the flavor off-diagonal part of the density matrix, which, I mean, unless you've been staring at plots like this, it doesn't make a whole lot of sense. But the point is that, so if we look at this right here, this is very good at visualizing wave fronts of flavor transformation. And so what we see here is there's largely planar structure, and that's because this is reflecting the fastest growing mode. You can look at the distance between planes of the same color. Those are planes of the same phase. That tells you your wavelength, which matches exactly what we'd expect from the dispersion relation. And you can also look at the growth rate, and that matches the dispersion relation. And so once it becomes nonlinear, once these off-diagonal elements become comparable to the diagonals, the instability saturates, and you're left with a nonlinear mess. You can then look at, if you average over the entire domain, you can say, okay, I started off with primarily electroneutrinos and antineutrinos. How much of each flavor is present at the end of the simulation? And so this is showing a collection of different simulations with different angular structures of the distribution. You can imagine this is looking at different points in a supernova or neutron star merger. And we can see that while in some cases, if you have the right conditions, you can completely mix flavors so that you have equal distributions of all three flavors. But in general, that's not true. In general, it's going to be somewhere between no flavor transformation, in the case that there's no instability, and complete flavor mixing. And so these models that completely mix flavors, we expect that to be an overestimate of the effects. And that's good news and bad news. Good news because it means that the simulations that we're doing are closer to realistic if we don't expect flavor to change completely. But it's also bad news because it means that we have to think a lot harder on if we want to treat this realistically, how do we actually treat the flavor transformation in a way that's believable, given that it really does depend on the angular structure of the distribution. So then, of course, being surrounded by some hardcore simulators, the question is, how hard could it be to just do the problem? Don't worry about any inferring subgrid models or anything like that. Just do it. So I want to look at some of the length scales involved. And so this is showing a particular profile from a one-dimensional supernova, just because you can't do a one-dimensional plot of a merger. So this vertical line is the shock front. it's at 175 kilometers or so. The protoneutron star is at a couple tens of kilometers, and this dashed line is just showing the radius. It's just r versus r. So if we look at the length scale for collisional processes, it looks something like this. So deep inside of the core of the protoneutron star, it's very optically deep. You have your mean free path is very short, but as you go to smaller densities, your mean free path gets increasingly long. And this is what classical neutrino transport tries to solve. It tries to solve the decoupling of neutrinos from this dense matter. Now we can look at some other length scales, like the separation between the particles. And the separation is very, very small. You can also look at the de Broglie wavelength, which is related to the momentum of the particle, and the size scale of the wave packet representing each of these particles. And those are much, much smaller. And now we don't try to simulate particles on the scale because it would be crazy to do that. There's far too many particles and the distances are way too small. But it's precisely this huge separation of scales that says that hydrodynamics and this local model of neutrino matter interactions is valid, because this large separation of scale says that approximation is very good. So then what about the flavor transformation? We can look at the length scale associated with the vacuum oscillations, and from the oscillations induced by the interactions with matter, and the oscillations introduced by the interactions with background neutrinos. There's, in some cases, these there's still some separation of scale. In general, these it's something like a factor of 10 to the 6, 10 to the 7 between the collisional length scales and the flavor transformation length scales. So the flavor transformation happens much, much faster. So in this case, it might be kind of marginal as to whether one could come up with a good approximation that treats the separation of scales. But in regions where it's large enough, the hope then is that that this large separation can allow us to treat the physics approximately with good confidence. But if you were to try to do it directly, you'd have to multiply you'd have to have a resolution of 10 to the 7 finer, which is a cost of 10 to the 28 more expensive, which is not an exascale problem. That's just a hopeless problem. So we're not going to do that.
So isn't here the different color somehow correspond to the two terms in the transport equation? Is that they are not separable?
So these the three colors here, the vacuum neutrino matter, all of those are the farthest right term, so the quantum mechanics term.
Okay. So there's no this collision term.
Yeah, so the collision term, that's the dashed black line.
Oh, okay. So anyhow, you can now simultaneously consider the big different length scales.
Mm-hmm.
Okay. But
Yeah.
in reality, is that they still affect each other.
Yes. Yes. Yeah, it's absolutely true. So if you leave a quantum unstable distribution long enough, that the collisions will modify it. But yeah, the collisions in general are much, much slower than the flavor transformation. There can be exceptions. If you have sufficiently high energy neutrinos, that the collisional length scales can become much larger, but the collisional length scales can become much smaller. Okay. So I'm almost out of time. Fortunately, I said the most exciting stuff. I will just very quickly mention that in addition to trying to do things very accurately with particle and cell method, there's a lot of interest in doing things approximately as well, just because by doing approximate methods, we're able to simulate things much more efficiently, which allows us to do a larger number of calculations in parameter space that you couldn't do with very fine detailed calculations. So like I mentioned, hydrodynamics, you can close hydrodynamics by applying an equation of state. In the case of neutrino transport, instead of modeling the transport of each particular neutrino, you can model the evolution of the energy density and the flux, and close this with something that's qualitatively similar to an equation of state. But it's it's not actually well known. You just come up with something that's reasonable and you plug it in. And so this is the so-called analytic moment closures, where you write some function of the energy density flux, and you pretend you know what the pressure is. And so that's clearly a wrong approximation, but you can use it to do much more efficient calculations that are that you can verify against more accurate methods. And so we've started doing that with, so maybe I'll talk about this tomorrow. So this is, you can talk about how well these analytic closures actually work for general relativistic situations like mergers and supernovae. The answer is they don't work very well, and I can quantify that, but maybe I'll just do that at coffee tomorrow if there's nothing else going on. But what I want to talk about more is applying this moment method to quantum kinetics. So we can use this moment directly to directly evolve the radiation field with moment description, which is something that some work that was started several years ago by people like Adam Burrows, and we've recently picked it up and applied it to a method in a couple of different codes. This first one here is just simulates the radiation of neutrinos away from a supernova. The black line is a full multi-angle calculation. The colored lines are 1 and 2 moment calculations. And the upshot is that they can produce very similar results. And this is something that we were not at all expecting, but at least in certain cases, it's surprising how well these approximations actually can perform. You can also look at this in neutron star mergers. And so in this particular case, which we've simulated we took a radiation field out of a neutron star merger, and we simulated it both with the particle cell method and with a moment method in 3 dimensions. And they both have very good agreement in the growth rate of the instability. And so you can model the instability with moment methods. The end result for how much of each flavor is significantly different, but it is exciting that instability is modelable with kinetics. Now, the particular choice of closure is something that also there's a lot of work that has to be done on that. But it's at least possible, and it's an exciting avenue for future research. And I won't talk about that unless somebody asks me. All right, and with that, so the main point is that we want to combine accurate treatments of the transport of energy and lepton number of neutrinos with reliable treatments of flavor transformation in order to really understand the dynamics and the nucleosynthesis in explosive astrophysical environments, to answer some of these big questions in physics and astrophysics. And with that, I'd be happy to take any questions. Thanks.
So the first question I would have to ask is, so this little box that you showed, remember, is like 80 centimeters, something.
8 centimeters, yeah.
Yeah. So it's just a wonder that this is a PEG simulation had the problem of a multi-scale problem. So how can you? But you said this. I think the last slide you showed this neutron star merger is very large length scales, but you also said some PEG simulation. So how you could do that?
Yeah, so you look at the conditions in one particular point, and so you essentially you carve out that little piece of space, and you simulate that little piece of space, ignoring the rest of everything else.
I see.
Yeah. So
okay, and another question is you mentioned that only this electron neutrino affects this neutron fraction in the ejector. So how this instability would affect the fraction?
Yeah. Okay. So that's a good question that I should have explained in more detail. So naturally, if flavor transformation, so in neutron star mergers, there's much more electron flavor neutrinos than other flavor neutrinos. And so if you transform flavor, you decrease the abundance of the electron flavor neutrinos. And so that decreases the rate at which neutrinos interact with this ejecta. Now that can, depending on the situation, that can either increase or decrease the eventual electron fraction of the ejecta, depending on whether there's a hypermassive neutron star what the ratio of energies and abundances of the neutrinos is, how fast the matter is being ejected, which determines how long it's able to interact with that irradiation of neutrinos. So in terms of generally, we expect that by removing electron neutrinos, that we're able to preserve more neutron-rich ejecta, but that's not a global. That's not always the case. So yeah, I wouldn't offer a clean, intuitive answer.
So this fraction may vary from one mercury one to another.
Yes.
Mercury one, but quite significantly.
Yes. Yeah, I think so.
Okay, thanks.
Yeah.
Can you comment a bit more on how big of an effect you expect this to have on the ejecta compared to, like, including the fast Weber transformations or neglecting them compared to, say, the other kinds of uncertainties that you might encounter in predicting these ejecta?
Yeah, that's a good question. So I mentioned a couple of things. I didn't mention all of them. So there's just like the numerical treatment of radiation transport. And so at least the calculations that I've seen so far, both ours and other groups, show that there's a significant impact from flavor transformation. But I would say that it's not as significant as, say, uncertainties in the nuclear equation of state. And perhaps similar to uncertainties induced by approximate radiation transport schemes. So yeah, I would not call it the largest uncertainty. It's, like you said, one of several significant ones.
Yeah, but that's interesting just to kind of contextualize it. Thanks.
Adam has a question.
Yeah. Alan?
Yeah, okay, Sherwood, that was an interesting summary. That's very interesting that this paper what you're doing with Gale is coming out soon, if it hasn't already come out. I'm very much looking forward to it. I have a couple of questions. The first is, I worry about when you're using a moment scheme and you have discretized in energy, or if you're doing a multi-angle scheme as well, and you've discretized an angle, there's a significant dependence of fast flavor conversion on the relative angles of neutrinos. And there's an energy dependence as well. And I worry about averaging over the angles and the energies to get a reasonably reasonable result which has fidelity to the gross energetics and the average properties. In other words, the stiff dependence on relative angles and energy needs to be averaged over if you hope to translate this to a high performance computing environment and get results that have some reasonable fidelity to nature. Mm-hmm. Sorry for the long question.
Yeah, so I will provide a small correction that is fortunately optimistic. If we're talking about just fast flavor instability, there actually isn't significant dependence on the energy. The energy dependence comes in from the vacuum term, so that's the relative size of the mass and the energy.
Well, there's the spectral swaps that might be important as well.
Yes, so that's from collective flavor instability, which is that's an effect that comes from matching the potential from the background neutrinos and from mass. In the case of fast flavor instability, that's just from neutrino-neutrino interactions.
No, I'm just thinking about trying to get the results for the general case.
Yes, yeah. So if you want to do it completely generally, yes, it's much more daunting. But that's why I think the regions where we know that it's unstable to fast flavor instability, but it's too far interior to be relevant for the collective oscillations. That's exciting because we don't have to worry about the mass. And so we can do it with a single energy group, and it's valid.
Okay, that would be interesting. When is your paper coming out?
The goal is Friday, but we'll see.
Okay, well, that's good. As you may know, Gail and James and I and a number of others are involved in a proposal that, if funded, would try to address this coupling between the fast flavor conversion physics and supernova and merging neutron star physics. David's involved as well.
Mm-hmm. Yeah, that would be very exciting.
It'd be good to talk offline if you have some time to come over here, or we can Zoom or do something like that. So let me not hold up everybody else's questions, but maybe we should talk in the next day or so.
Yeah, that'd be great.
So since the scale of this flavor instability is so small, you might think that all you really need to know is what the nonlinear outcome is. I mean, it'll reach some saturated state where the flavors are mixed at some level. And so is there any way that, so that sort of suggests a subgrid model where, all you really need to know is what fraction of each flavor you're going to get given the initial conditions, because instability is just going to go so fast, it doesn't matter to the dynamics, it's so fast. So is it any prospect of being able to map out parameter space so that you would be able to predict what the final outcome is for any given input, and then therefore be able to incorporate it into the calculations?
Yeah, so there's two ways of doing that. There's the smart way and the brute force way. I'm not smart, so I'm working on the brute force way. But people have done some preliminary analytic work where if you have some restricted class of models, you can predict with some fidelity the result of the outcome. For general distributions, it's currently not known how to do that, but it's possible that analytic treatments can advance to the point where that prediction is possible. But yeah, I mean, these calculations are quick enough to do a variety of models, and so I
just scope out parameter space.
Yeah.
Provide maybe a fitting function or something at the end.
But this collision term, you have to include it analytically, right?
So I guess in what Jim is suggesting, we would treat the collision term just with the transport, so it's already being done, and you would just change flavor very quickly, and it happens quickly enough that you don't think about the
Coupling between them.
Right. Yeah. So, and there could be regimes where that's not quite accurate, and subgrid models are not perfect, and so that I think would be an avenue for future investigation, because I don't know. I know, like I said, that they do happen in the same place in the same times in mergers, but I don't know whether that would be a perturbative effect or.
I see some analogy to mean field and one small scale.
Right. Sure. Yeah. Any very small process.
Yeah, I should also maybe mention this is all mean field quantum mechanics. There's other people who work on many body quantum mechanics, and so we already closed the quantum mechanics at the mean field level. So there's an approximation there too.
Yes, so one of my main takeaways so Carolyn asked about sources of errors, and you kept on bringing up the errors introduced by approximate radiation transport algorithms. But I was kind of surprised throughout the entirety of your talk. I didn't see one plot that convincingly showed me that, for example, M1 is performing extremely poorly. So I think that your one plot that you went to was comparing Monte Carlo to M1, and you're showing YE. And you said that there's some discrepancy between the two, but what was that, like the 10% level? And so,
yeah.
So I'm curious if you had to point to one place where that error is showing up the worst, where is that?
Yes, there's a lot of clicking, sorry. So I think, so there's this, in the polar regions, this is particularly bad. So one of the big challenges with understanding the radiation that we saw from GW 17017 was this blue fast component of the light curve that appeared before the long red part that we expected from heavy elements. And so the question is, where did that come from? What processes launched a much faster, much more optically thin component of ejecta? And so that's especially where this radiation transport, the radiation transport is important, because that comes largely from the polar regions, which is where moment schemes are not very important. And so that's when you move when you have significant matter at these large electron fractions, that is conducive for creating a more blue component because you can't form as large of elements. And so the concern is that if this has significant impacts on how much of that, how neutron rich that polar ejecta is, that can have a significant impact on how well we understand that blue early component of the ejecta.
So sorry, just to remind us, these are dynamical merger calculations done with Monte Carlo the whole way versus M1 the whole way. They're not snapshots. They're
right. Yes. Yeah.
dynamical calculation done with different approaches.
Yes, and these are relatively short duration simulations. So to really get the full impact, you'd have to simulate for a much longer time because there's a lot more disk outflows. But, yeah.
And this is of the disk or of the like dynamically launched ejecta?
So the filled in parts are the polar ejecta. The rest of it is you can see very, very neutron rich stuff. That's all dynamical. So the dynamical ejecta is largely in the equatorial direction. So if you select the poles.
Okay, so not okay.
All right, looks like it's 12:10, and let's continue the discussion over lunch, and let's us thank Sherwood.